So in a simpler type of projectile motion question, very often you will have basically a level ground, and you will have a projectile that's being launched and with some speed, let me call that v naught, at some angle theta. And there will be something about like where it lands, and there are many different questions that can be asked. It can be about the range, how far does it travel horizontally before landing back down, or it can be about some other question. But this is the kind of standard projectile motion setup. And the other complications we can introduce, you will see them done in other harder questions. So let me do this question here, and I will save the drawings for the next question because a lot of what I draw will still be useful. So for this question, it says an astronaut on Mars. Oh, so that's gonna limit, it says acceleration of gravity on Mars is that number, 3.7. So I'm just gonna write it on screen so that I don't forget. My acceleration due to gravity will be minus 3.7 meter per second squared. So astronaut on Mars kicks a soccer ball at an angle. Okay, so I'm given the angle. That's good to know. With some initial velocity. Okay, I'm given the initial velocity. That's good to know. 16 meters per second. If the acceleration is 3.7 meter per second squared, what is the range of the soccer kick on a flat surface up? So we are being asked for the range. Now, you can certainly look up the formula in the textbook. There it's again standard setup. Your textbook is a way of demonstrating how to solve. It's done that. Let me just do this from scratch. I think it's a good skill for people to learn. And if you haven't seen an example elsewhere, hey, here's one example. So you start by breaking your motion into x horizontal and the y component. You can do it because the motion along these two perpendicular orthogonal directions are independent. That's one. Two, the horizontal component of motion is particularly simple, so it'll simplify your problem solving. So the main thing I need to break down is the initial velocity. I have x component, I have a v naught x, and I have the y component, v naught y. And this, let me draw a larger version of that triangle here. If you imagine this right triangle, this is where you use that SOHCAHTOA. Your v naught y is on the opposite side to the angle. So from SO, which is sine of an angle is opposite of our hypotenuse. You solve this for opposite side, then opposite side is hypotenuse times the sine of the angle. So from that, you can say the y component of velocity is the magnitude, the hypotenuse of the velocity times the sine theta. And using similar reasoning with the cosine of an angle is the a adjacent over the hypotenuse. You can say the x component of velocity is v naught cosine theta. And sometimes people have this temptation to always associate y with the sine, x with the cosine. I guess for projectile motion it'll probably work, but I recommend getting into habit of drawing these right triangles and identifying the angle and dealing with the sides properly, because every now and then angle will be specified in a weird location and you might make a mistake. So with the velocity broken down, now I'm ready to write down my kinematics equations. The x component, as I said, is really simple. X component of the position as a function of time is, let's say I'm setting my origin here. This is my x equals 0. So 0 plus, I have the displacement due to this initial velocity. That's going to be v naught cosine theta times the amount of time plus, and this is the simple part, horizontally there's no acceleration. So x is equal to that. The y component of motion is a little bit trickier. I'm going to say my starting place, that's where my y is equal to 0. So again, 0 plus, you have the displacement due to y component of velocity, v naught sine theta times t. And now you have displacement that's coming from the acceleration. and that's 1/2. It's plus 1/2 times acceleration. I see that acceleration is minus, so I'm gonna put in minus 1/2. The value of acceleration 3.7 meter per second squared times t squared. I didn't want to put g in there because then I might confuse myself with a 9.8. So this is your system of equation, and the general physics problem solving works this way. The very first step is you kind of have to come up with a system of equations. That's basically compiling the information you know. Sometimes you have to use some laws of physics in writing those down. Sometimes you have to use kinematics equations that you have memorized. So once you have some number of equations, this is the check that you need to do. You need to check that you have the right number of equations. Here I have 2 equations. So what I'm hoping for is I have only 2 unknowns. So I'm looking for range, which will be my sort of final position. So this is an unknown. Let's see, initial velocity I know. T, I don't think I'm given that anywhere when it lands. So T is another unknown. Okay, 2 unknowns so far. Y position, now this is where you have to think carefully. If you are thinking of Y position in general terms, then sure, you don't know it. Then you are running into an issue because you have 3 unknowns, 2 equations, not enough equations. But as you visualize this motion and think about it, do you know the Y position when the ball lands? The answer is yes, you do, because when the ball lands, your Y position should be 0. So this is not an unknown for this specific situation we are dealing with. This Y position, you can say when the ball lands, is gonna be 0. So with that realization, you have 2 equations, 2 unknowns. In theory, it's solvable. And you know, depending on the equation, sometimes it's quite complicated to solve, especially quadratic equation. You have to use quadratic formula, it's complicated. But let me write down the simplified form of this equation, and maybe I won't have to use quadratic formula. From equation 1, let me just plug in r for the final x position. R is equal to v0 cosine theta times t. Okay, not all that simpler. Let me look at the second equation. 0 is equal to v0 sine theta times t minus 1/2, that number 3.7 meter per second squared times t squared. And this is where, if you have this realization, that really helps. If you imagine multiplying everything through by 1/t, arguing that you are not really interested in t equals 0, which actually does satisfy the equations, but not interested in that, you are interested in this, then this 1/t, because the left hand side is 0, left hand side is left at 0, and on the right hand side this cancels a factor of t in every term. So you have t here, so you actually have a linear equation. So you have a linear system of equations, 1 and 2. And I think you see me demonstrating use of Sage Math in some other homework help videos. If you want to use Sage Math, great. Learn how to use it and use it. Here, let me just do it by hand. I think I can, and in solving system of equations, you want to have a plan. And here, my plan is, I'm trying to solve for r eventually. So that's the very last thing I want to solve for. Because whatever I'm solving for intermediately are the ones I'm going to be eliminating. So I want to solve for t first. I can do that in the second equation. I think if I'm solving for this t here, then I need to move that over. Then I have 1/2 the number, 3.7 meter per second squared, times t is equal to v0 sine theta. And I can divide up by this entire collection of numbers. Then that'll cancel on the left hand side. On the right hand side, I'll have 1/2 3.7 meter per second squared. And you can simplify as you go or not simplify. I do think practice simplifying things are valuable, but sometimes it's just numbers. So yeah, do what feels natural to you. So this is the tool that I'm going to use to eliminate t from my equation 1. I can plug this in for t there. That'll give me r. So doing this as r is equal to V naught. And let me just not simplify anything this time. I'll just plug in all the numbers into O from alpha. V naught cosine theta and then the t. And I guess I could have actually plugged the, let me actually do this. I'm gonna plug in the numbers to get a numerical value here and then plug it in here. This is kind of an easier question, so this is possible. Every now and then there will be some system of equations where things are kind of tangled together. So you have to, plug it in and then resolve for some unknown that's still here. But here I don't have to, so let me use the fact that this is a simpler question. So I have V naught 16 meter per second. I'm gonna put in all the units. O from alpha will work out the units. I don't really have to, but let me do it this time. Sine of 34 degrees, that's my initial angle, divided by 1/2 times, let me just make sure this is grouped. I have 3.7 meter per second squared. That's the entire denominator for t. So if I say press enter, that'll give me the t. And yeah, it gives me time in seconds. That's what tells me that I probably didn't make an algebra mistake. 4.84 seconds. And I can actually just change the search here. I can just keep all this entire expression here. That's gonna become my t, and just put in the things in front. I need the V naught, 16 meter per second. Oops, just that, times cosine of 34 degrees. Times this entire expression is still t. That kind of helps reduce rounding error and kind of keep things organized. Have that, okay, all looks like understood me correctly. 64.2 meters. So that's the answer, 64.2. Let's make sure, yeah, okay, that's correct. And one of the nice thing about O from alpha is that when the question changes, what would be the range of the Sankey on the moon where the gravity is 1/6 that of the Earth? In this expression, all I have to do is just change that one number. This 3.7 instead of that, 1/6 of Earth, okay, 9.8 divided by 6. And I think that's slightly off from what the actual gravitational acceleration on the moon is, but I'm just going with what the question is telling me. In case there's any difference, hopefully following what the question is literally saying helps me get a better answer. 145.3. Or I can round it. I should be able to round it to 3 significant figures. So 145. I feel not as comfortable with that because of the leading number 1, but it should still work. If it doesn't work, let me know, because it really all the questions have tolerance of 1%. So as long as you are rounding nearest correctly, it should really work.